Let's continue our discussion on oscillations with a couple of further cases that we haven't looked at just yet, and also finish up by looking at some examples. So far we've looked at simple harmonic motion in a pendulum and also in a mass bouncing up and down on a spring. In the case of the pendulum, we could look at an angular displacement either side of equilibrium, and in the case of the mass on a spring, we could look at the linear displacement of a mass either side of some equilibrium point. What we didn't look at was the case of a rotational system, or in this case, a torsional pendulum, a twisting oscillator. In this particular case, we take a line and attach it to a solid disk. The disk is then displaced from some 0 point and released. This will cause the disk to oscillate between two positions, two angles. These could either be measured in radians as usual, or you could put them in degrees if you wished. But the disk will oscillate between plus theta and minus theta about some single rest point. So this is a case of angular simple harmonic motion, where this disk is bouncing back and forth in this fashion. Now, in this particular case, we have to look at a slightly different force. In the case of the mass bouncing on the spring, we could look at the linear force, and that force was proportional to K, a spring stiffness constant. If we looked at the case of the pendulum, then we were really just looking at L and G. But in the case of this disk, there's going to be a restoring torque, a torque that wants to take this disk and make it swing back towards equilibrium. And that's going to be given by the twisting force of this wire about the center, or torque is going to be equal to negative kappa times theta, and this kappa is what's referred to as a torsion constant, and it depends on the length and the diameter of the particular material that this particular line is made out of, and this will cause the disk to rotate through theta either direction as it's twisted. If you take a look at the form of this particular formula, tau here, torque, the twisting force, is equal to negative kappa theta. This is very similar to Hooke's law for a linear spring of F equals negative kx, where k here was the spring constant and x was an extension of the spring. Here, torque is negative k times theta, how far away from equilibrium this particular line has been twisted. Now if we look at a standard oscillator, T was equal to 2 pi root m over k for our mass bouncing up and down on a spring. Now if we look at this situation, we'll have a very similar equation that can be reported for this. Now for a rotational system, we aren't just looking at the mass. If we're to just look at the mass of the system in a mass on a spring, that's fine. But in the case of this disk, the distribution of mass is what matters. And in that case, we can replace m with an inertial term I. K here is the spring constant and can easily be replaced by kappa, being the torsional constant. Consequently, T is equal to 2 pi root I over kappa is the equation that you need to use if you're looking at the torsional pendulum. Now, I here is dependent on the distribution of mass in the system. So usually it's a task to calculate I or to look it up from tabulated values. Now a minor issue here is if you do not have a tabulated value for I, then you might have to actually integrate over the shape of the object and find the mass distribution and find any inhomogeneities in the mass and plug the function into here before you proceed. So in the case of a simple pendulum, we had a mass bob m, a single sort of point mass here at the end of a string, which would then swing back and forth through some angle theta from equilibrium. The restoring torque with an angular displacement is always torque is equal to negative L, this being the angular momentum, F sine theta, which gives us I alpha. substituting in for alpha in terms of m, g and I, and we end up with the typical equation for a pendulum of 2 pi root L over g. Now, a second case of the pendulum, which uses a very similar principle to the one we just discussed, which is looking at a distribution of mass through an object rather than a point mass, is a case of a rigid pendulum. By rigid pendulum, we mean instead of having a string with a mass at the end of it, what we actually have is something more like a meter stick or a cylinder, anchored at one end and then allowed to swing back and forth. In a case like this, we cannot just use t equals 2 pi root L over g. What we have to look at here is the distribution of mass through this pendulum. So, anywhere you see a solid object that is oscillating, you will always have to engage with an inertial term, I. And that I, as I said, is unique for every single shape. So the angular velocity, in the case of a physical pendulum as it's referred to instead of a rigid pendulum, is omega equals square root of mgl over I. Consequently, our period again is 2 pi I over mgl. Then this is a particularly nice, pleasant one, where we could actually see that this would be a relatively homogeneous distribution of mass. The mass per unit length here could actually be defined as a lambda, and this would actually be quite a simple one to solve in terms of I. But you could see more unusual situations, things like a bowling pin shaped object here, where there's definitely more mass here than there is here at the origin. And in cases like this, you'd have to look at a much more complicated distribution of mass. When you do this, the distance that you need to consider is from the origin to the center of mass, not the overall length of the entire pendulum. So for small angular amplitudes, which is true of any particular simple harmonic motion, once you start getting to large angles, things start to break down a little bit. But for any relatively small angles, you can have a situation where the period here, t, is 2 pi root I over mgh. H being the distance from the origin here, the pivot point of your pendulum, to C, the actual center of mass. So this h is not the complete length of your pendulum, it's the distance from the pivot point to the center of mass. The forces, as you can see, sine theta for the restoring force, cos theta for the displacing force, are essentially the same as they would be in a standard pendulum. What you always need to figure out is what is I. And of course, like I said, I differs for each and every shape. Here's a few typical inertias. People who have done the first part of my class have probably seen these before, but in most cases, if we were looking at an exam or an assignment, I would probably give you a value of I. If you were doing this in reality, you'd usually have to do some kind of integral to determine the distribution of mass in your object. So let's take a look at one of these. Here's our rigid pendulum. We have some overall length here, and then we have a distance h from the pivot point O to the center of mass C. Here's a standard pendulum just for comparison, where we'd be looking at the length L0 and looking at the oscillator either side of equilibrium. Again, we're still looking at the oscillation between equilibrium, but we have different parameters. So, what is the period of oscillation? Our meter stick is swinging about a pivot point at one end, distance h from the stick's center of mass. Well, you should immediately have gone for t equals 2 pi root I over mgh. Now, we know that this is a stick, a nice uniform stick, so if we go back to the previous slide here and we look up or a table like it, and we look up the value of I, we'll end up with 1/3 ml squared that we can substitute straight in for I. This is a standard kind of value for a long, flat plank. This is going to be divided by mgh if we assume that the mass distribution in this is uniform. That means the mass per unit length is the same throughout this stick, which it should be for a well-engineered lab meter stick. Then we can say that the center of mass is going to be exactly halfway down this stick, and that's where this 1/2 L comes from. L is the total length of the meter stick, and H here is going to be halfway down the stick. If we look at what we've got, here's M, here's M, here's L, here's L, we've got the factor of a third, a half, and we'll end up with 2 pi square root of 2L over 3G. We can now substitute in for these values. We know G is always 9.8, we are located on the Earth for this one, and of course L, it's a meter stick. And that's a very common problem if we're looking at something like this on an exam, is quite often people overlook the point that this is a meter stick and not know what L is, when clearly L is going to be 1 meter. So this is going to be 2 pi 2 times 1 over 3 times 9.8, which will give us 1.64 seconds. So part B says, what is the distance L0 between the pivot point O of the stick and the center of oscillation P of the stick? Well, we know from the previous part that T was equal to 2 pi root L over G, which is equal to 2 pi root 2L over 3G. That means if we take a look at this, here's L, here's G, this will boil down to L0 being equal to 2/3 of L. We can cancel G out here and we'll end up with 2/3 L. Substituting in, we'll get 2/3 100 centimeters, which will equal 66.7 centimeters or 0.667 meters. Let's take a look at a system of oscillating springs. So this is really looking at some of the material we saw in Oscillations 1 in the previous set of slides. Here, a spring stretches 0.15 meters when a 0.3 kilogram mass is suspended from it. So here we're looking at part A in terms of the vertical mass on a spring. mg is acting downwards, and of course F is acting upwards from the spring with some spring stiffness constant times the extension of the spring. F equals negative kx. The spring, after we've done this part, stretches 0.15 meters when a 0.3 kilogram mass is suspended on it. The spring's then set up horizontally with the 0.3 kilogram mass resting on a frictionless table. A little unrealistic, but does simplify the calculation. What it's really saying is there's no damping in this situation. So the mass is then pulled so that the spring is stretched 0.1 meters from the equilibrium point and then released. We're going to determine spring stiffness constant, the amplitude of the oscillation in the horizontal case, the magnitude of the maximum velocity, and the magnitude of the maximum acceleration of the mass. So in terms of spring stiffness constant, this one should be relatively simple. We saw that F was equal to negative kx, so a value for k can easily be obtained from the vertical case, where k was equal to F over x0. This will equal mg, as the mass was just allowed to fall under rest, under gravity, until it came to rest, so this will be mg over x, the x0 being the equilibrium length of the spring. So this will be 0.3 times 9.8 over 0.15. This will give us 19.6 newtons per meter. That's our value of k. Part B states, what's the amplitude of the horizontal oscillation A? Well, we know the spring is stretched horizontally 0.1 meters from equilibrium. So the question really is, what's the amplitude of this oscillation? Don't overthink it. The amplitude of the oscillation will simply be however far you stretch the spring. So A will equal 0.1 meters. Let's take a look at part C and ask, what's the magnitude of the maximum velocity? Well, the maximum velocity of our system, in this case with a mass on a spring, will always occur as the mass passes the equilibrium point. At this particular point, there is no spring potential energy to work with. All the potential energy has been given to kinetic energy. So we can look at the total energy and compare this to the energy at equilibrium. What we're really doing is comparing half mv squared for the mass to half ka squared, the potential energy stored in the spring. So half mv squared should equal half ka squared. Rearranging for v, if we want the velocity, we can say this will be the amplitude times root k over m. This will equal 0.1 meters times 19.6 over 0.3 kilograms if you go back to our values, which will give us 0.808 meters per second. Part D asks, what's the magnitude of the maximum acceleration of the mass? Well, acceleration, there's only one real place to go here. We can't really get there from energy very easily without doing some differentials, so I just straight out use F equals ma. The force is going to be greatest at maximum amplitude, of course. By F equals kx, the maximum extension of the spring means the maximum recoil force you'll have. So x is equal to a equals 0.1 meters. So the maximum acceleration will be F max over m. Continuing with this, F max, of course, will be kx or ka in our case, so we'll end up with ka over m, substituting our values of 19.6 and 0.1 respectively, 0.3 kilograms, and we should end up with about 6.53 meters per second per second. So let's take a look at a case of a spider's web. Here a spider of mass 0.3 grams waits in its web of negligible mass. Any movement on the web causes the web to vibrate with a frequency of 15 Hz. We want to estimate the stiffness constant K for this web. Now, we know that T is equal to 2 pi root m over k if we're looking at a situation of like a spring. If we assume that the spider's web behaves as a spring, then we can take the inverse of the period, giving us the frequency of 1 over 2 pi root k over m. We want k, so let's rearrange and get k is equal to 2 pi f squared times m. At this point we can simply substitute in. We have f of 15 Hertz or 15 inverse seconds. We have m here of 0.3 grams. So substituting in, we'll end up with 2 pi squared 15 inverse second squared times 3 times 10 to the minus 4 kilograms. We have to convert this to kilograms, otherwise our answer will not come out in newtons per meter. So for our next example, we're going to look at a large motor in a factory. As this motor is running, it will cause the factory floor to vibrate up and down at a frequency of 10 Hz. The amplitude of the floor's motion near the motor is about 3 millimeters. And this is the kind of calculation you really have to do if you build an industrial building and don't want it to collapse when you turn all of the machines on. Because if everything is vibrating and you end up with, say, the resonant frequency of the building, you might end up with your building collapsing. So let's estimate the maximum acceleration of the floor near the motor, and we'll assume that motion is simple and harmonic, the simplest thing we can do, and that the maximum acceleration is where F equals kx is a maximum, so where x is equal to the amplitude. And we'll use the acceleration from F equals ma. This means we can say A max is equal to F over m. F is equal to Ka, so we can substitute in all of our standard definitions, which will equal K over m times A. Substituting in, we can say that K over m is equal to 2 pi f squared. Consequently, our maximum acceleration will be F over m, which is K over m times A, which is 2 pi f squared A. This will equal 2 pi squared times 10 squared times 30 times 10 to the minus 3 as we convert our millimeters out, and this will give us 12 meters per second per second. So this essentially is the acceleration of the system. So yet another example of an oscillating system. We have a system starting with x equals a cos omega t, which is the standard equation for the displacement of a particle in an oscillator. We're going to have x equals 0.3 meters, so a is 0.3 meters, and the cosine of omega t, so we have the angular frequency of our system. We want to determine the object's amplitude, frequency, period, maximum speed, and maximum acceleration, all from this one equation. Consequently, if we want the amplitude, as I've said before, don't overthink things, A is just 0.3 meters, straight out of our equation. The frequency, well, here we have to use the variables that we have. 2 pi f essentially is going to equal 8 seconds here from our angular frequency. Omega equals 2 pi f for linear, converting from the angular to the linear frequency. That means f will be 8 over 2 pi, which will give us 1.27 Hertz. Now we have to do b to get c. The period is simply the inverse of the frequency, or 1 over 1.27, giving us 0.79 seconds. So we're determining quite a lot of things from this base equation for the displacement of the object. Part D was the maximum speed. The maximum speed from our prior definitions is simply 2 pi AF. Substituting in and multiplying through, 2 pi times 0.3 times 1.27 for our frequency will give us 2.4 meters per second. And finally, the maximum acceleration. Where we always want to go for acceleration is essentially F equals ma. We can say that the maximum amplitude is essentially F over m, or Ka over m. This should actually be small a here. It has been capitalized. So this will be K amplitude over mass here. Substituting in, we can take this and say K over m will therefore be 2 pi f squared times a. This will give us 2 pi squared times 1.27 times 0.3, which will give us 19 meters per second per second. Our final example deals with a block on an inclined plane. Here we have a block with a weight, or as I like to term it, force of gravity of 14 newtons, which can slide, again without friction to simplify things, on an incline at an angle of 40 degrees. It's connected to the top of the incline by a massless spring of unstretched length 0.45 meters and spring constant 120 newtons per meter. So a fair amount of information in this question. Part A. How far from the top of the incline is the block's equilibrium point? And Part B wants to know if we give this a slight movement from its equilibrium point down the incline and let it go, what's the period of its oscillation? So in terms of Part A, we once again are dealing with a spring. Anytime we're dealing with a spring, the first place you should always go is F equals kx. Unfortunately, F isn't exactly kx right now due to gravity because it's going down an incline. So kx is equal to mg sine theta. If we want to find out how far from the top of the incline the block's equilibrium point will be if it's hanging down the slope based on the spring holding it in place, then x will be mg sine theta over k. Substituting in, we have our 14 newtons, our angle of 40 degrees, and we have our k of 120 newtons per meter. That'll give us 0.075 meters. But this isn't the total answer. What this represents is essentially whatever x is, the extension of the spring. It's not the distance from the top. So it's been displaced by equilibrium, from equilibrium. So the distance from the top of the incline to the block is 0.45 plus 0.075, which is going to give us 0.5252 meters. So we do have to add the unstretched length of the spring to this value. Part B, remember, stated if the block is pulled slightly down the incline, so given a little bit of a displacement down the slope and released, what's the period of the resulting oscillation? Well, this essentially is 2 pi root f over k, or m over k I should say. So we'll have to find out what m is. So this is going to be 2 pi 14 newtons over 9.8, which essentially is going to return our m over 120 newtons per meter. This is going to end up cancelling and give us 2 pi root k over m, and that'll give us 0.686 seconds. So we're dealing with a gravitational case, so the effect is identical here whether the spring is vertical or at an angle, so it will still end up with a period of the same order, of the same value, if it's hanging down the slope or hanging vertically.